Buyur Erman.
Hello, everyone. The second speaker of today is Adilhan. He's from Boğaziçi University. Adilhan has worked on class field theory, which is one of the main areas in number theory. The title of his speech is Statements of the Main Theorems of Class Field Theory. Adilhan.
Thank you very much. In this talk, I will try to state the main theorems of class field theory. First, I will give some notions from algebraic number theory, then state the theorems in terms of the ideals, then for the local fields, and lastly, in terms of the ideals. Now, class field theory deals with the global fields and local fields. Global fields are the finite extensions of the rational numbers or function fields, and local fields are the fields with an absolute value function. And under this function, under this topology by this function, it is locally compact and complete. An absolute value is a generalization of the usual absolute value function on R for a field satisfying these conditions. And if it satisfies this condition, we will call it a non-Archimedean. And the discrete value function on a field K is a function satisfies these conditions. And with a discrete valuation function, we have an absolute value which is non-Archimedean. And with this induced metric from an absolute value, if we take its completion for this field number field K, it will be a local field. And now we will focus on number fields. A number field has an integer, has a ring of integers. This ring is a dedekind domain, and hence any ideal has a decomposition into unique prime. Any ideal has a decomposition into unique primes, into prime ideals. And we call an ideal a principal ideal if it is generated by a single element. And since this ring is a dedekind domain, every prime ideal is a maximal ideal. And if we take this quotient, we will have a field, which is called the residue field. And we extend the ideals into fractional ideals by taking their fractions. An ideal class group is this quotient. On the left-hand side, we have the group of ideals under the multiplication for the ideals. And on the right-hand side, we have a subgroup, which is the principal ideals. And this quotient, ideal class group, is a finite group. Now we focus on the field extensions. Let's L over K be a field extension. Since L is also a number field, a prime ideal of K will decompose into prime ideals in L, and the powers of these Qs are the prime ideals, are called ramification indexes of Qs. And if a ramification index for a Q, Qi, is equal to 1, we call Q is unramified over the prime ideal P, and if all the ramification indexes are equal to 1, the P is called unramified in L. And since L is a field extension, the residue fields, by taking the residue fields, we have a residue field extension, and the degree of this extension is called residue field degree or inertia degree. And there is a strong relation between these two numbers, ramification index and the inertia degree, and the field extension. If we take this sum, we get the degree of the field extension, L over K. And now we assume L over K is a Galois extension. Then all of the ramification indexes are equal to each other, and likewise the inertia degrees. And we know that there are only finitely many prime ideals that ramify in an arbitrary number field extension. Almost all of the prime ideals are unramified. And now we define a norm map between these two ideal groups for the extension L. Take a prime ideal in L that lies above the prime ideal P. Then this norm map sends the Q to the prime ideal P to the residue field degree. And we extend this map into all of the ideals by this multiplicative property. And now we again assume L over K is a Galois extension. Then this Galois group acts on the prime ideals Q laying above the same prime P. And under this action, we call the decomposition group of Q the stabilizer of Q. And then we have a surjective homomorphism from the decomposition group of Q to the Galois group of the residue field extension. And we call the kernel of this homomorphism the inertia group of Q, and we get this isomorphism. And all of the decomposition groups for the primes Q laying above the same prime P are conjugate subgroups. And in the case of an abelian extension is a Galois extension such that the Galois group is abelian. All of the decompositions group are equal, and the decomposition group has an order E times F, and the inertia group has an order E, the ramification index for Q. And now we introduce another notion from algebraic number theory, let K be a number field. Then there is a strong relation between the prime ideals of K and the absolute values on K. Ostrowski theorem says that any absolute value comes from either prime ideals of K or from real embeddings or from the pairs of complex embeddings. And thus we know all of the completions of K. We call an equivalence class of an absolute value a prime of K or a place of K. And with these primes or places, we define a modulus. A modulus is a finite product of primes on K. The M0 part is the M0 part consists of the prime ideals, finite prime ideals, and the M infinite part consists of the embeddings. A complex embedding has an order 0, a real embedding has an order 0 or 1, and the prime finite prime has an order positive, has a positive order. And now, before the main theorems, we define the class Ray class group. Let us denote by IMK the ideals that are co-prime to the fixed modulus M, and let us denote by KM1 the elements of K star such that whose principal ideals are co-prime to the modulus M, and they are congruent to 1 modulo M0, and their real embeddings are positive. Then we denote by RMK the principal ideals that are formed by the elements of KM1, and we take the quotient IMK over RMK and define and call it Ray class group for the modulus M. This is some kind of a generalization of the ideal class group. And now we have an important isomorphism, not isomorphism, an important homomorphism. The class field theory deals with the abelian extensions of global fields or local fields. Let L over K be a finite abelian extension of the global field K, and take a modulus such that all of the primes that ramify in L are in this modulus, and if a prime is not in this modulus, it is unramified. And let's Q lie over P, and it was unramified, hence the ramification index is equal to 1, and thus the inertia group is a trivial group. And then we have this isomorphism between the decomposition group of Q and the Galois group of the residue field. On the right hand side, the Galois group is a cyclic group generated by an element called the Frobenius element, and we take its pre-image in the decomposition group and denote it as PLK and call it also the Frobenius element. Now we denote by P because all of the decompositions group are equal to each other, and then the Artin map defined as this map, it takes a prime ideal to its Frobenius element, and it's extended to all of the ideals co-prime to the modulus M by this multiplicative property. And we have a less definition before the theorems. A congruent subgroup for the modulus M is a subgroup of IMK such that it contains the RMK. Now, the main theorem says that the first main theorem for the ideal theoretic part is reciprocity law, let K be a global field, and take an finite abelian extension L over K. Then there exists a modulus M such that the Artin map for this modulus M, this extension, we have an isomorphism between these two groups. Now, this is an important statement because on the left-hand side, we have an information about the arithmetic of the field K. These are just the ideals. And on the right-hand side, we have an information about the extensions of K, the Galois group of this field extension. Now, by taking the quotient by RMK, we can rephrase this statement via the Ray class groups. And the second main theorem is an existence theorem for a modulus M and for a Ray class group, not Ray class group, for the congruence subgroup. For this modulus, there exists a finite abelian extension L over K unramified at the primes outside of the modulus M, such that the congruence subgroup is equal to the kernel of the Artin map. Now, then we have this isomorphism. This is also an important isomorphism, since it's like by looking inside the K, we can see the extensions of K. This isomorphism says this kind of. Then in particle C is equal to RMK. Then we have an extension such that Artin map induces an isomorphism between the Ray class group and the Galois group of this extension. Such fields are called Ray class fields. Now we state the theorems for global fields in terms of ideals. Now we state these theorems for the local fields. Let K be a local field. Then there exists a continuous homomorphism theta K called the local Artin map from K star to the Galois group of the maximal abelian extension of K, such that for any L over K finite abelian extension, the theta LK, the local Artin map induced by the restriction for the Galois group, satisfies these two conditions. I skipped the first one, and the second one says that theta LK, the local Artin map, is surjective with the kernel norm image of the L star, inducing this isomorphism between these two groups. Again, arithmetic and the extension. Local Artin map comes from the Lubin-Tate theory and the local Kronecker-Weber theory. And the second major theorem for the local part is the existence theorem. It says that for any finite index open subgroup N of K, there exists a finite abelian extension such that this subgroup is equal to the kernel of the local Artin map. Now we state the main theorems for the local part and the global part separately. We want to unify these two theories, and we haven't talked about the maximal abelian extension of K for K a global field. Now the ideal-theoretic part will fill in these gaps. Let K be a global field. We define the ideal group as this. It consists of the elements called ideles, such that they are the sequences of the elements of the completions of K, and such that for almost all places of K, AV is in the unit of this completion. And we put the restricted product topology on the ideal group. This is not usual product topology. In this topology, we have much more open sets than in the usual product topology. And we have three important maps. The first one is from the ideal group to the ideal group. This is a surjective map. The second one is the diagonal embedding of K star into the ideal group. And the third one is the embedding of the completions of K into the ideal group. And hence, with these maps, we see that the ideal group considers all of the completions of K and the K itself at once under the restricted product topology. And we define the ideal group, ideal class group as this quotient. This is the analog of the ideal class group for K. Here, the K star is the embedding in the ideal group. Now we define an analog version for the ideal case of the norm group. Ideal norm is a map from the ideal group of L to the ideal group of K. And with this definition of ideal norm, we have these commutative diagrams. These commutative diagrams say that this norm map is compatible with the other norm map previously defined for the ideal case and for the fields. And before the main statement, we defined the global Artin map. Now, this proposition says that there exists a unique continuous homomorphism theta k called the global Artin map from the ideal group to the Galois group of the maximal abelian extension of K, such that for all L over K finite abelian, and for all W lying above the prime V, we have this commutative diagram. Now, above map is the local Artin map. These are the local fields, and the below map is the global Artin map induced by the restriction for the Galois group. And now, by this diagram, we see that the local class field theory is embedded in the ideal-theoretic version. Okay. And now the main theorems for the ideal-theoretic part. Now, the first main theorem is the global reciprocity law. It says that for a K global field, the global Artin map satisfies these two conditions. The first one says that the K star is in the kernel of the global Artin map, and the second one says that for any finite abelian extension L over K, the global Artin map induces this isomorphism. Now, again, on the left-hand side, we have an information about the arithmetic of K, and on the right-hand side, we have an information about the extension of K. Now, by, again, taking the quotient by K star, we rephrase this this property, this isomorphism, in terms of the ideal class groups. Now, the second main theorem is the existence theorem. Let K be a global field. Then this theorem says that for any finite index open subgroup N of the ideal class group, there exists a unique finite abelian extension L over K such that this subgroup that we choose is equal to the Artin map, is equal to the kernel of the Artin map for that finite abelian extension. And now we can connect the ideal theoretic part with the ideal theoretic part with these definitions. This construction will give us an analog of the Ray class group for the ideal part. With this definition, this is the analog of the ideal. This is the analog of the Ray class group for the ideals. With this definition, we have these isomorphisms. On the left-hand side, we have the ideal Ray class group, and on the right-hand side, we have the ideal theoretic Ray class group. And the main theorems of class field theory say that the quotients of the Ray class groups are equal to the Galois groups of the field extensions. Now, with these isomorphisms, we can connect the ideal theoretic part with the ideal theoretic part. And this is the end of my talk. Thank you very much.